Good afternoon, IT sensors. My name is Chani Park, who is studying for master's degree at Kwangwoon University, South Korea. Thank you for granting me this presentation opportunity. Today, I am going to talk about highly stable calcium ion selective flexible sensor based on treated PEDOT PSS transducing layer. This is outline. First of all, I will introduce our research background and review the previous works with short overview of PEDOT PSS. Then, I will show research challenges with our approach. The materials and device fabrication will be explained with figures. Finally, I will present experimental results and summarize contents of presentation. Recently, as ion sensors are combined with wireless technology from medical diagnosis to environmental analysis, many researches in various fields are being published. Especially, calcium is one of the major ions that make up living things. Also, the possibility of self-medical diagnosis and environmental monitoring has been shown by continuous detecting calcium ions from biofluids and water. From these recent studies, we can recognize it is essential to determine calcium ions for human physiology and environmental analysis. And for long-term monitoring, the stability of the sensor is very important. There were several studies about ion sensors in an inexpensive and popular way. Colorimetric and electrochemical sensors are representative. However, colorimetric sensors are not quantitative and they require additional conversion process to be quantitative. In addition, ambient light can affect the performance and it is disposable. On the other hand, the electrochemical potentiometric ion sensor shows quantified results also because it's not disposable. Electrochemical sensor is more suitable for long-term monitoring. In potentiometric ion sensors, the solid contact material used in the ion-selective electrode ISFE determines the sensor performance. The use of metal and low-dimensional materials needs complex fabrication process like photolithography and CVD, and it's high cost. Accordingly, a conductive polymer that can be easily synthesized is recently drawing attention as a promising solid contact material in sensors and actuator spheres, showing a CAGR of 8%. Among the numerous conductive polymers, PEDOT PSS has become promising solid contact material due to its excellent properties. However, despite these advantages, as you can see its structure on the right side, the ionic bonds between the conductive PEDOT and the insulating PSS form a coil-like structure resulting in a small grain size. So when PEDOT PSS is formed into film, it has low conductivity and is very hydrophilic due to excess PSS and randomly oriented grains. As you can see, the potentiometric ion sensor consists of reference electrode and ISFE, including a transducer layer and an ion selective membrane. When the sensor's ISFE contact with the analyte, water molecules and target ions can pass through the ion selective membrane. At this time, the higher hydrophilic properties of the transducer layer, the more easily water molecules are pushed to form a large water layer. And this aqueous layer causes a potential drift over time. Therefore, reducing the hydrophilic properties of the solid contact material is way to be stable. And it is our approach. PEDOT PSS can be modified by simple treatment with polar solvents or acid. It has been found these treatments will result in conductivity enhancement, larger surface area, and improved stability by phase separation, crystal reorientation, and excess PSS removal. For easy fabrication and safety, we used ethylene glycol EG as co-solvent of the PEDOT PSS water dispersion. This method changed the coil-like structure and small PEDOT core size to a linearly expanded structure and large core size with excess PSS removal. I will briefly introduce the working principle of the sensor. The calcium ions in the analyte and the potassium ions in the membrane are exchanged at the interface between ISM and the analyte. Then calcium ion forms a complex with 3 calcium ion pores and moves to transducer layer. At this time, an electric potential is formed across the total ISE, and the potential difference with the reference electrode is output. After that, water rays gradually form over time, but this can be suppressed by using our approach, resulting in improved stability with thin water layer. From this slide, I explain total fabrication process. To prepare transducer layer, ethylene glycol of 6 weight % was added to the PEDOT PSS water dispersion and sonicated for 10 minutes to achieve a homogeneous solution before use. And then, to prepare the calcium ion-selective membrane, 3 regions were added to THF solvent, and then plasticizer was added. Then the solution was stirred for 30 minutes. Now I will explain how to fabricate sensor. First, prepare a clean PET film and then attach a pattern PI tape mask. And then carbon paste was printed and the PI tape mask will be removed. The prepared treated PEDOT PSS was dropped on the ISE and dried at 100 degrees C for 4 hours. Finally, the prepared calcium ion-selective membrane was dropped onto a working electrode and dried overnight. Now, I'm gonna show about experimental results from this slide. The ethylene glycol treated PEDOT PSS film showed a slightly larger water contact angle of about 83 degrees than the pure film. It means treated film is less hydrophilic than pristine film. And from FESM images, it was found pure PEDOT PSS on carbon electrode is thick and its surface is smooth. On the other hand, the surface of the ethylene glycol treated PEDOT PSS became rough. From this, we can predict that the surface area would have increased slightly. Electrochemical characterization of the modified electrodes was performed by cyclic photometry in ferricyanide solution. The conductive polymer on carbon showed great redox peak. Moreover, modified electrodes with ethylene glycol treated PEDOT PSS showed more higher peak current. This means EG-treated PEDOT PSS has better charge transfer property with larger surface area than pristine one. For optimization, electrodes with PEDOT PSS treated by different weight % of ethylene glycol were performed by CV. The highest performance was obtained at 6 weight % of ethylene glycol. Finally, to confirm the conductivity enhancement, we prepared thin film for voltage sweep. As a result, we confirmed the conductivity was remarkably enhanced. Now, these 4 figures shows performance of the fabricated sensor. The experiments were performed with DI water containing different concentration of calcium ions. The fabricated calcium ion sensor showed linear response of a slope of 31.9 millivolt per decade in log scale. To confirm its selectivity from interfering ions, sodium, potassium, ammonium ions, major components in biofluids were chosen for electrolytes. The fabricated calcium ion sensor showed negligible potential change for interfering ions. Finally, to confirm our research can improve the stability, a long-term potential stability test was performed. From this test, the EG-treated calcium ISFE showed better stability with drift of 0.34 millivolt per minute. I summarize my presentation. We successfully developed and tested the EG-treated PEDOT transducer layer for potentiometric calcium ion sensor. The fabricated sensor exhibited excellent sensitivity, linearity, and strong resistance to interfering ions. And also, the EG-treated PEDOT transducing layer proved enhanced potential stability, but it still makes a big drift now. Finally, it is found simple treatment of PEDOT paves the way for highly stable and reliable ion sensor for long-term monitoring. In future work, we will hybridize it with pH sensor and develop real-time monitoring system in real samples. This research was supported by following organizations, and I'm grateful to all authors and my research lab ASA members for technical discussion and support, and IEEE Sensors officials for holding this conference despite the corona. Thank you for your attention.